Good evening, everyone. Thank you for coming out. Most of you probably know me, but if you don't, I'm Chris Wenzel, the current president of the LIAPG, and very grateful to have you and our guest speaker here tonight. We have a few slides on LIAPG business that we're going to get through quickly, and then we'll move on to the presentation and document your attendance. So with that, let's get into it quick. First of all, we'd like to thank our 2022 corporate sponsors. Those include PW Grosser, Alpha Analytical, Castle Environmental, EnviroTrack, ERM, and Island Pump and Tank. And if you're not familiar with any of these organizations, you can go to our website, and there on the homepage, there's a scrolling banner with each company's logo. If you click on that logo, it will take you to that company's website, and you can check them out a little more. But we surely appreciate the support and the continued participation and partnership with us. A little bit about upcoming events and things going on. We're going to continue to have these Zoom meetings. We usually have them the third Thursday of every month. And we're always perpetually looking for speakers. In fact, we only have one more committed at this point, and that's on June 16th next month. Paul Grosser is going to do a webinar on natural disaster resiliency. That is definitely going to be a Zoom. We are exploring venues to do an in-person event. We haven't been able to do them in quite some time, obviously, and we're hoping that maybe this little mini surge in COVID will go back in the other direction, and we'll be able to have that, and there'll be enough interest. That presentation is also approved for professional development hour credits, 1 hour. So look for the announcement. It'll come out for registration, and we'll specify in there if it's going to have a in-person component to the event. We're always looking for speakers, so if you have something interesting to present, we sure would like to hear from you. I'll leave that commercial there. The board has also been working on putting together some field trips for this year, and it looks like we're going to be able to get a guided tour of the Hall of Gems in the American Museum of Natural History in the city. We were thinking that we would follow it up with a, bring your own food picnic lunch in Central Park across the street. So stay tuned for that. There'll be more if we can actually make it happen. And then in August, we are hoping to renew our annual canoe trip and picnic that we've done several times in the past few years, and on the Nissaquag River, unless we change the location, but that is the candidate location at this point. So stay tuned if you like doing that. We've always had a good time. We'd sure love to see you come out. The board of the LIAPG meets monthly, usually the first Monday of every month. The next one is the 6th of June. If you're interested in what goes on or getting involved with the organization on a committee or possibly joining the board, we are an open organization. Just get in touch with us through our email, liapgprez@gmail.com. Send us an email and we'll set you up with that. Right now, we're still doing them online, but that may change in the future too. A little bit about our sister organizations around the state. There's the New York State Council of Professional Geologists that covers the whole state, and they are putting together an event in October called Geology Days. The intent of it is to promote the professional practice in the state and create a venue with multiple speakers over a 2-day period. The 17th would be a arrive and a mixer and socializing, followed by 2 days of technical presentations. I sit on the board as a representative from the LIAPG, and I can tell you that those folks are working hard on making this a real good event. So keep your eyes out. You will see an LIAPG email blast about it because we support our sister organizations, and those include the Buffalo Association of Professional Geologists, Central New York, Right now, those two organizations don't have any specific events scheduled for the coming months, but you should check their websites because, like us, they have some pretty cool stuff done online, or if you're in the area, you can participate in person. Generally, they're monthly also. HMCA, the Hudson Mohawk Professional Geologists Association, has a trip planned in June. It's their summer outing, and it's basically a field trip to it's in the Saratoga Springs region, and the two locations that they're going to visit is Stark's Knob, which is a pillow basalt formation from an old volcano, and then Lester Park is a Cambrian. It's a park that's a Cambrian fossil reef. Pretty cool stuff if you've ever been there. There's lots of sponges and stromatolites and things like that. So also, again, also there's the Northeast American Institute of Professional Geologists. They just had an event yesterday that's done and gone. They don't have anything listed, but check out their website because there's a lot of good content that everybody's doing these days. We mention every month also in Pennsylvania, the Council of Professional Geologists has a pretty robust program of courses and classes that are free to members, but for a small fee, you can also participate in these things. And you can see here they've got May, June, and they take the summer off, and then in September they've got another one presented on on emerging contaminants, particularly PFAS. So that's a cool thing to check out also. SUNY Stony Brook has geology open nights. They generally have 3 or 4 a semester, and it looks like this semester's closed at this point, but I'm sure that as the summer nears end, they will post a fall 2022 schedule. That's another cool thing. They have some pretty interesting topics and some pretty fascinating researchers going on there. If you are pursuing a professional geologist license at this point, besides meeting the educational and experience requirements, you also have to pass the Asbog exam. There's 2 components to it. There's a fundamentals and a practice portion, and that's offered twice a year in October and March. And you can see here on the slide set, we've got the next 3 scheduled testing events and the application deadlines. If you have any hope of participating in the October event, the deadline for your application is June 15th. And if you haven't started, you should, because it takes a little bit of effort to put the whole thing together. And you can find out more information at asbog.org. And now we're going to get to our main event. Many or most of you registered also to receive credit, professional development credit for participating in tonight's event. And the way we're going to document that, because documentation is required, is 2 parts. One, in the upper right-hand corner here, we've got a code, LIAPG 214. Would appreciate it if everybody would just, in your chat box, just say, "Hi, I'm here," and put that code in, and we'll ask for the same thing at the end of the presentation to verify that you hung around and participated in the whole thing. So that's my speech for tonight, and we'll move on to the main event. We're very, very pleased and lucky to have Dr. Caitlin Ahrens here. She's a postdoctoral program fellow for NASA at the Goddard Space Flight Center. And, I had made a request for this topic in particular, looking at some off-planet geology, and it's near and dear to my heart. So without any further ado, I'm going to stop sharing and allow Caitlin to share her screen and kick things off. I particularly like the little slide you put together, Caitlin, where you did the "I love LIAPG" with the little heart on the moon. Very nice.
Thank you. Yes.
So, go ahead.
All right. Fantastic. All right. So hi, everybody. So I hope everybody's ready for some space geology because it is, oh dear. trying to share my screen, but the other screen is still being shared.
Is it?
Mhm.
Thought
I
it
can
went away.
see I can see your Excel file.
Oh, wow. Stop
Oh,
sharing.
beautiful black
There it
hole
goes.
picture there. Okay, hello.
There
I
we go.
lovely image of the black hole there.
Sagittarius A.
All right, yes, we love to see it. Love to see it. Oh goodness. All right, so mysterious, marvelous cryogeology. So I'm mostly going to be talking about just ice, but how weird and cool ice is on other planets. So we're going to kick off real quick with just very basics as to what in the world kind of ice are we even dealing with here. And the weird part about the solar system is that ice is not constant throughout the whole solar system. And it's really interesting to say that there's ice at Mercury, which is the closest planet to the sun. There's certainly ice on Mars, and then certainly ice that makes up everything else from Jupiter and beyond. But what's all mixed in? What kind of ices are we dealing with? It's not just H2O. So that all has to come together as to where are we specifically in the solar system. And so myself and others who study cryogeology, we all have our own very specific favorite spots in the solar system. Like I really enjoy being out at Pluto and a little bit at Neptune. When you get to around Uranus, chemistry starts to get a little weird. When you're at Jupiter and Saturn, there is some weird chemistry going on there. So that's a bit of a headache. And then currently I'm also working on ice on the moon, and I'll talk about a little bit about that later here in a bit. And then, like I said, ice on Mars and Mercury are separate folks that work on that. But another interesting thing too about H2O ice is think of it as almost different kinds of minerals we have here on Earth. You change up your temperature and pressure, and your mineralogy changes. So we're no longer just looking at the chemistry, whereas say amethyst and citrine, they're just pretty colorful pieces of quartz. But if you up the temperature and pressure of quartz, you start to get different kinds of minerals. It's still silicon dioxide, but you're having different polymorphs. And so water ice really confuses us because there are 19 different crystalline types, all depending upon your temperature and pressure here, or how I like to call it, the different yoga poses of your hydrogen and your oxygen atoms going on here. So all depends upon whether are they like trying to do jumping jacks, or are they trying to do stretches one way or another, you know, downward face dog or something. Yeah, just all these different kinds of poses can make up the different kinds of ice. And that's just H2O. That's just water ice. There's different crystalline types of methane ice. There's different crystalline types of nitrogen ice, and the list goes on and on. So we have to create charts like this piece of headache here. So it depends upon your temperature and pressure. This is just water ice, just to show how very complicated each of bits and pieces of all this water ice can really be. Now, for outer solar system folks, we don't really have to worry about vapor liquid that much. We really have to focus on the solid. So icy surfaces, you're dealing with very, very, very low pressure, very low temperature. So down below there, icy surfaces. If you want to go more into interior oceans on some of these ocean worlds, so Europa, Enceladus, even Ganymede, you're dealing with higher pressure water ice going on there. So like I said, not just H&O, it's not just water ice. We're dealing with carbon dioxide, methane, ethane, carbon monoxide, nitrogen. On Titan, you can have benzene, you can have acetone, so nail polish remover. It's everywhere on Titan, Saturn's largest moon. And I'll talk about Titan later because Titan is a very bizarre moon. But that's the wonderful part about cryogeology, is learning how do all of these mix together, and then what do they build? what kind of geology do they build upon? So cryogeology, essentially taking just very simple compounds. A lot of the compounds I just listed, the carbon dioxide and methane and ethane, you have your carbon, your nitrogen, your hydrogen, your oxygen, really not that complex. So taking just very simple ices and then making very complex geology, mountains, glaciers, volcanoes, stuff that seems to still be moving. So glacial systems are really quite interesting. Even tectonic faulting. So all of these different kinds of geology from just the simplest compounds is so fascinating. So that's mostly what I do at NASA, is to figure out what are some of these geologic structures and how can we figure this out with models? Can we figure some of this out in a laboratory? So I'm specifically a geologist, but I do want to make a mention that we're all different bits and pieces of cryo studies. So I work on the geophysics side of things, but I have to pay attention to the thermodynamics. I have to pay attention to the mineralogy. I have to chat with people who do way more chemistry than I do. There's also astrobio. Astrobiology is becoming a really big thing in planetary science. So how would some of that biology maybe be preserved in some of that ice? Astrophysics. And you would think astrophysics, like, that's just galaxies and black holes. What does that have to do with ice? Well, astrophysics people can help us understand our sun and what can the sun do to our ice. So we have to talk to heliophysics and astrophysics people and go like, hey, wait a moment, my ice is melting. What is the sun doing that's melting my ice? And then we have interesting conversations from there. So just giving a interesting example here as to just how fun cryogeology in a planetary NASA scientist point of view is. So let's just take Pluto, for example, here. So we get this lovely image from the New Horizons mission. It got to Pluto summer of 2015. And we see this is just the top lobe of Sputnik Planitia, that beautiful heart that everyone loves so much on Pluto. This is just the top load. And we can see how dynamic it is already, just how turbulent some of that liquid might actually be. And we see maybe a little bit of mountain work off to the side there. So we know that there's something dynamic going on, and keeping in mind that the temperature of what we're seeing at this point is, I work in Kelvin a lot. So we're seeing 40 Kelvin worth. So we're talking negative 400 some degrees Fahrenheit here. Very cold, but something is still so dynamic at that temperature. So from New Horizons data, we figure out, okay, we know what the chemistry is. We know there's nitrogen, methane, carbon monoxide, and water ice is just everywhere. So, okay, we know what the chemistry is. Now, can we recreate that in a laboratory? So this is an example of some ice mixtures at about 30, 40 Kelvin, very, very cold cryo chamber in this case, mixing ices kind of deal. Okay, can we recreate what we just got from New Horizons? Turns out, yes, in a sense. We're able to recreate some of those ice mixtures. Now, can we model it better? So this is just a graph of what happens when you mix methane and nitrogen together. Well, you get different kinds of mixtures going on here. So taking those different kinds of mixtures, can we then model different glacial systems and maybe all that turbulent moving and all that? Can we then model what we just made in the lab, which is based off of the mission data? So all of these have to work in tandem with each other. Now, there's times when we may not have any mission data or lack thereof, just very, very minimal mission data. That's okay. So great example there would be the Voyager data. Very, very limited Voyager 2 data specifically at Uranus and Neptune. That's okay. That's not going to stop us from doing laboratory work and modeling work based on just very, very few images. But it gets us all ready for, oh, maybe we found something we didn't expect in a laboratory. We didn't expect something out of a model. That can help I figure out like, oh, we need another mission. We need another mission to Neptune or Uranus, and because our models say something is weird going on with the ice, we need to get there now. So having all of this perfect trifecta going on here is keeps us pretty busy. Now sometimes ice tends to play by its own rules. Sometimes it's not always just pure crystalline solids. You can have two other interesting flavors going on. The first flavor here is called clathration, or just clathrates. So imagine, if you will, just a water ice cage, and it's trapping some sort of gas that's just bouncing around like crazy, going, oh, help, get me out. So the gas trapped inside is typically methane. We have actually a lot of clathrates here on Earth, mostly in Siberia and Alaska, but we also possibly have clathrates on Mars. And then we know that there's a lot of clathrates on comets as well. So clathrates are an interesting bunch though, but here's a lovely image around the Alaskan area of what some of these clathrates may look like. So they're very lightweight. They'll just kind of float up to the top because, again, they're just trapping gas inside. Also, a fun little tidbit about clathrates too, definitely be careful about these in a laboratory. They're extremely hard to make in the laboratory, but they're also really fun to light on fire, mainly because the methane will immediately go, oh, there's heat, I can escape now. And so the methane will immediately just start releasing, and it won't melt right away. So it's very bizarre to just light a snowball on fire and it won't melt right away. It's a very, very odd looking thing to behold, and so it's very fun, but safety first. So the second flavor that ices can play by its own rules here are called tholins. So tholins were coined by Carl Sagan when noticing that some of the moons of Saturn were very dark colored. And so he proposed, oh, there's probably some weird chemistry we don't understand that is being irradiated by the sun. And that's why it's dark. And so when we finally got to Titan using the Cassini mission, and then finally New Horizons at Pluto, we're realizing there's all this really rusty red ice, but it's not rust. There's no iron at this point in the solar system. So tholins are not naturally found on Earth. They are very much found on icy bodies. So think of it, tholins, as like sunburned ice. That's essentially what it is. You have very, just very basic chemistry hanging out in the atmosphere, minding its own business, and then wham, solar radiation just starts taking these apart like Lego bricks and then sloppily putting them back together with no instructions. It's almost like you're trying to build a Death Star and you end up building a dollhouse. Just very, very different Lego bricks going on. But because those Lego bricks then start kind of piecing together over and over and over and over and over again, that kind of chemistry makes the molecule itself very heavy. So it'll just fall like snow. So we see this all over the surface on Titan. This image of the Western hemisphere of Pluto, it's everywhere because it just fell like snow. So they are extremely difficult to make in a laboratory, but there are two specific laboratories that make tholins for planetary science. The first one being the Applied Physics Laboratory, APL, here in Maryland, and then the other one is in San Antonio with the Southwest Research Institute. So ice geology in at least the inner solar system, so Mercury, Earth, Mars, the moon, we have polar caps. You can have craters that can impact differently depending upon if there's ice. Frosted dunes. Frosted dunes are very pretty on Mars. I'll show you a picture here in a bit. We have glaciers here on Earth. not necessarily cryovolcanoes, maybe a little itty bitty volcanoes. So what I'm showing here at the bottom part here is some ice on the moon there. So all the little pretty blue speckles there, that's not the ice being that color blue. I wish that'd be cool. But no, that's just our like detection observations through several orbiters going like, oh, we know that there's like hydrogen, oxygen there. It might be water ice. Certainly cold enough. So that's kind of zooming in at the south pole of the moon here. So all these orange outlines here are called permanently shadowed regions, which is a little bit about what I work on here at NASA, is to figure out these are some really, really cold, deep craters on the moon. And so my job is to figure out what kind of ice. It's not just water ice. There could be ammonia, methane, carbon dioxide. So my job is to help figure out where some of that chemistry is, how cold can some of those craters be, because we want to send astronauts to this part of the moon eventually. And so we kind of need to get them prepared, and either avoid dangerous ices or go, hey, go to this spot. We want to know what kind of ice is over here. Off to the bottom left here is some frozen dunes. Now, frozen dunes on Mars, and this is on Mars, are really quite beautiful because Mars does have very short seasons, to be sure. But whenever the dunes get like a beautiful layer of frost, they have a very interesting bright sheen to them. So frozen dunes are very, very pretty, but they don't last long, but they'll freeze over again and in and out, they'll thaw. So outer solar system, this is where the meat and potatoes are of the talks. So we're getting into some really bizarre geology here. We have what's called fluted craters, as opposed to just, there's regular, boring, hole in the ground craters too, but fluted craters are really pretty. There's multi-ring craters. So multi-ring craters is you have something impacting the surface so hard that it ripples the surface. Now with ice, once you ripple it, it won't want to relax back. Once it ripples, it ripples. It'll stay there. So I'll show you a beautiful example of the largest multi-ring crater in the solar system here in a bit. You can mountain caps. You can still have dunes. Ice can still create dunes. Glaciers, different kinds of folding and faulting. So you have different kinds of tectonics, frozen lakes, and then cryovolcanism, which is my favorite part. So as a geophysicist, what does all these structures even mean? So again, part of my job is to figure out how sticky some of this ice could be, how bendy and flowy some of this ice are at different levels of the solar system. Could melting or sublimation be an interesting process here? Is there anything seasonal at some of these planets and moons? Turns out yes. And then erosions as well, so glacial erosions. But I want to kind of go through like what in the world is cryovolcanism, because this is a really cool topic, no pun intended here. So cryovolcanism, we had a workshop at this point quite a few years ago, 2018. But this was our very first a couple day worth workshop of cryovolcanism. We brought all these experts in Houston, Texas for a few days to just simply hash out what is cryovolcanism, because we all tend to have different aspects of what in the world is cryovolcanism, and they could be different on every different moons and planets in the outer solar system. And so did we end up with a final definition of what cryovolcanism was? Nope. Did we leave that workshop with even more questions and answers? Yes. Do we hope to have another workshop? Hopefully soon. But if anything, it got all of our wheels turning of like, oh, I didn't think about that, or oh, we need more experiments to do this with this temperature and maybe this kind of ice mixture. So there's different kinds of definitions here. So you can have different kinds of cryolava. You can have different kinds of eruption styles. So just to kind of boil all this down, though, is there's got to be just some sort of liquidy thing in the mantle of your moon or planet, and then those liquids need to migrate up to the surface somehow. And so by that somehow, it could be a myriad of different ways here. So it can be convection, so similar to our own mantle. You have stuff rising and then falling, and then rising and then falling, almost like a conveyor belt kind of deal. You can have an ascension of very warm ice. You can have melt lenses that would fracture the surface. So like little air pockets, if you will. Exsolution is a very fun type of mobility. So exsolution means bubbles. So we're thinking that exsolution bubbles are actually happening mostly on Titan, Saturn's moon. And then yeah, there's times when you can have very large fault systems, or even different kinds of fracturing systems and whatnot. Just break apart the surface and just let the liquids fly. So let's take a tour of icy bodies, or how I like to call pretty picture time. So let's get to it. Now, unfortunately, not much is done with Ganymede and Callisto. These are very much ignored moons of Jupiter. Ganymede doesn't really get that much love, unfortunately, but I will give you guys a little bit of a fun news here. There will be a Ganymede book to be coming out, I think, the end of this year, because I got to help write one of the chapters on bendy ice on Ganymede. So that was a fun chapter to write. Granted, it had like a billion equations on it, but hey, bendy ice gets its own chapter. All right. But unfortunately, Ganymede and Callisto, like I said, just do not get a lot of love here, but very, very beautiful moons. Ganymede is the largest moon at not only Jupiter, it's the largest moon in the whole solar system as well. And then Callisto, tiny, dinky little moon there. But we're probably thinking Ganymede and Callisto may have had what's called a relict ocean world, which means it used to have an ocean underneath it, probably something very dynamic and slushy. But that slush starts to gunk up after a while. All the salt can no longer be exolved or anything. So the salt will start building up and building up and building up, so that the slush just becomes too solid, and then no more ocean. So that's what we're probably thinking is going on here with Ganymede and Callisto. But just some really pretty pictures at Ganymede, though, so we can just see how bizarre some of this ice looks, of just how curvy and bendy it is. You have a bit of an impact, and then all the rays. The brighter the ice is, the fresher the ice is before it starts getting irradiated and whatnot. Some interesting scallopy type terrains on Ganymede as well. This is on Callisto. So this is Valhalla. So Valhalla is the largest multi-ring basin in the whole solar system on tiny dinky little Callisto, and Callisto has this monstrous thing. But you can just see all the rings. This thing rippled the ice so much to create Valhalla. All right, so onward to Europa. Europa is definitely a fan favorite, to be sure. And there's always the debate on do we want to go to Europa? Do we want to go to Enceladus? Because they're nearly the same, except Enceladus is a little bit more complex than Europa here. But happy to chat Europa, of course. So Europa, you start to see some of this, the reddish stuff again. So this is not necessarily tholins, though, because Europa does not have an atmosphere. You need an atmosphere for tholins. So what in the world is all this red stuff all over the place? It's actually salt. A lot of this is actually very simple salts, table salt. So sodium chloride is on here, magnesium chloride. There's even some bromide chlorides on here as well, I think. So different kinds of salt can also be irradiated and sunburn and make that kind of reddish color as well. But a really cool feature about Europa, if anybody out there is a fan of the X-Men, so this is a really fun kind of nickname we have for this part of Europa, though. So we call this the Wolverine effect. So Wolverine, though, the guy with the shiny claws, one of his mutant superpowers is self-healing, self-rejuvenation. And so Europa, and we're realizing different icy moons do the same thing here too, most of the time. But Europa is expert at this, Olympic gold medalist for this one, is that if an impact hits Europa, Europa's ocean is still so slushy and dynamic that that ocean will immediately kind of ripple up that impact and no longer make a hole, but instead it just kind of gloss it over or scab over and essentially self-heal its surface. So all the fish scale looking textures that you see here are considered fresh wounds on poor Europa, though, but it's self-healed. So we'll actually get to a much larger example of something that is currently in the process of self-healing later. But Europa is still the gold medalist for that rejuvenation process, which we, again, just very informal nicknaming that we call it the Wolverine effect. Another cute thing, so this is where the salt really kind of plays a interesting little chemistry trick on us too, is that we have salt domes here on Earth. Salt domes also appear and in the same way on Europa. So we have planetary geologists go out to different kinds of salt domes. There's a lot of beautiful salt domes out in the Middle East too. And to study how in the world are salt domes formed on Earth, can we make assumptions as to how they're formed on Europa as well? All right, so we're gonna hippity hop over to Saturn, which certainly has the weirdest collection of moons in the solar system, in my opinion. So we're gonna start with the largest moon of Saturn, which is Titan. Boy, is it a weird moon, because it is not only just a large moon, it's the only moon with an atmosphere. It has beaches, it has lakes, it has canyons, it has islands, it has dunes, it has river systems, it has climate zones, it has weather, it has rainy seasons. It's such a bizarre moon. So the image that you're seeing here is this kind of a weird conglomeration of different Cassini images, because the actual picture of Titan is this little fuzzball here. Well, obviously you can't see much through that mess. So it took us a really good while to kind of get through some of Cassini's instruments to really peer through those clouds and see bits and pieces of geologic structures here. Now, have we mapped the entire surface of Titan? No. Have we even barely scratched the surface of all the geology of Titan? I don't think we've even scratched the surface on that. But all the really darker streaks that you see here, all those are tholins. All those are beautiful sweeping dunes sweeping across the equatorial plane there. The kind of pinky gold stuff that you see kind of at the top there and a little bit at the bottom there too, those are some of the clouds reflecting sunlight going on there. So we do at least have some black and white images and radar images from the Cassini spacecraft whenever it would go through over Titan. So we are able to see that there are dunes here. So this is a little bit of what some of the dunes look like here. Now, all of this white crusty stuff on the left image here, all this little white stuff here, we realize that it kind of looks like salt, but we know that there's no sodium and no magnesium this far out in the solar system, at least not on the surface anymore. So what's interesting here is that benzene and other little weird complex chemicals can act the same way as salt. So you have benzene and ethylene and acetone mixing with the water, or actually, not water. It's too cold for water. I'm not going to spoil what's the liquid here yet, but it'll mix in with the liquid present on the surface of Titan, and then that liquid will evaporate and leave behind the residue. So similar to the salt beds of Utah. I mean, it's the same process, which is really cool. It's not salt, it's salt-like. Now, liquid. I made the mistake that I said water ice. Water is very much a solid block of ice at these temperatures on Titan. We're talking 90 Kelvin, so we're at negative 300 some degrees Fahrenheit here. Still very cold. But what could possibly be liquid at those temperatures? And turns out it is methane. Ta-da! So methane actually works the same exact way as water, which is so bizarre at this particular temperature. It creates the rivers, it creates the lakes. There's flooding on Titan as well. And so it'll evaporate, it'll make the clouds, it'll rain methane and then fill up the lakes again. So it's almost like the water cycle here on Earth, except with methane. But it's the same process. It's so cool. So this is an interesting little picture of a possible cryovolcano with some like lava channels coming out of it on Titan. This was an interesting surprise. These are labyrinths. So I was on a team with some Cassini folks to write a paper as to what in the world could these possibly be. And the only logical explanation we were able to figure out is that these are just labyrinths. These are just very giant ice wall mazes with no means to an end of a solution kind of deal. But we're still puzzled as to what could have made these things, because they may look shallow. They're like, oh, you know, maybe river systems. The issue here is that imagine you have 3 football fields high ice walls, so ice walls of Game of Thrones in a maze. A simple water channel is not going to make something that big. So maybe some sort of faulting is probably going on here and whatnot. But back to the pretty lakes and islands here. So this little guy gave us quite the headache dozens of years ago now. So, you know, we see a picture of the beautiful lake system here, and then this little island appeared, and then it disappeared. Then it reappeared, then it disappeared. I think it reappeared and disappeared like 3 different times, and we're like, is something wrong with our camera? Is there like a fuzzy thing on the camera? What in the world is going on here? And we realized that, oh, it's flooding. That poor island is getting flooded over, and then the shores will the waters will go down and then up and then down and then up. So that poor little island. So we called it Magic Island for like the longest time. All right, so Enceladus, another fan favorite here. So very much a cousin to Europa, a little bit more dynamic geology in this case though, because the southern hemisphere of Enceladus is extremely active and extremely warm. And I'll tell you how warm it is here in a bit, but the beautiful light blue stripes that we see here, the official geologic term for these are called sulky. That's a weird name. So the nickname we use these are called tiger stripes. So the tiger stripes of Enceladus. Now, the interesting part about these tiger stripes is that they are geysers, very, very active, beautiful geysers. And they're still going on and off to this day, or we assume. There's nothing around Saturn anymore for us to confirm at that point, because Cassini is now a dead mission. Oops. But when Cassini was just about to get over one of the geysers, the thing about Cassini, it's an orbiter. You can't slow down an orbiter. I mean, you could, but that's not a good idea. So we're like, oh, great, Cassini's going to go straight through this geyser. Let's hope it survives. But while it's going through this geyser, let's just turn on all the instruments. And what Cassini basically did as it zoomed through this geyser is what we like to call sniffing. So it essentially just got a big whiff with all of its instruments as it flew through the geyser. And it was able to confirm so much stuff for us. So not only were we able to confirm that it was water ice that was spewing out, it was also incredibly warm, which meant that there was a very warm active ocean. And it had the same salinity as the Pacific Ocean here on Earth. That's so cool. So this really, really gave us the roadmap toward understanding what oceans are out there in space. So now NASA has what's called ROW, or the Roadmap of Ocean Worlds. So ROW gives us kind of our priorities as to, okay, we need to send missions to these ocean worlds. What kind of instruments do we need? How do we even know that there's an ocean there? What other instruments can we confirm with the ocean chemistry, the ocean physics? Are there any kind of weird core and mantle dynamics going on at these moons? All of these questions. So other weird little moons of Saturn that I'm just gonna kind of go through very briefly, but happy to answer any questions about some of these other moons as well. So we have Abitus, the walnut moon, mainly because of that little ridge on the equator of Iapetus. So yeah, you know what? It looks like a walnut. Do we know how this ridge was formed? Nope. Do we have a few guesses? Yeah, sure. Yeah, we have a few interesting guesses there, but I don't think we're close. Hyperion, this is a really adorable, cute little moon. Probably smaller than the size of Manhattan, actually. So very, very small little moon. But we call it the sponge moon. Well, I mean, yeah, just look at it. Poor thing. Helene, even smaller than Hyperion, but gorgeous, beautiful, looks like paintbrush strokes on the surface of Helene. Okay. Now we're gonna go through some of the moons of Uranus. I'm not gonna go through all the moons of Uranus. They're all strange and beautiful and weird, but I'm only gonna mention two of the weirder ones here. The first one is Ariel. Probably the best pictures we have of any of the moons of Uranus between Ariel and Miranda that I'll show here in a bit. But Ariel has some beautiful tectonic faults going on here. So just the surface just cracking and ripping itself apart, and just these big blocks of ice all over the place. Beautiful. And then poor Miranda. So Miranda is a bit of a headache because we have no idea what happened to Miranda whatsoever. Its poor nickname is called the Frankenstein moon. So we think that this poor little moon probably got blasted but didn't get blasted far enough apart, and it tried to paste itself back together, but very poorly, blindfolded, wearing 3 pairs of gloves with duct tape and honey. Yeah, anyway, so Miranda is just a very, very bizarre looking moon. All right, so Triton. Triton is a captured moon of Neptune. So it is Pluto's Kuiper Belt cousin. So Triton actually used to be part of Pluto's neighborhood until Triton just got a little too close to Neptune's orbit there, and then just got captured by Neptune. So give it a couple thousands of years into the future, Triton is slowly spinning into Neptune. So at some point, Neptune will eat Triton. But for the time being, this is truly the only image we have of Triton from Voyager 2 back in 1989. So really not that many images of Triton, unfortunately, but really some really weird geology nonetheless. So we get some weird squiggly looking ice here. We do have some beautiful low-lying basins that are probably cryo lava, so just not geysers or anything, but just puddles of just water ice there and nitrogen. Now these things in the south, this is the south pole of Triton, so we're looking at Triton upside down here. These little black streaks here really kind of gave us a head scratcher. And it actually wasn't until many years later that finally, I believe it was a professor out of St. Louis University of Washington, finally figured it out and was like, oh, these are geysers. These are just little itty bitty geysers. And you might be wondering, wait a moment, hang on, they're like dark colored. Like, how does that work? Turns out nitrogen and carbon dioxide, when mixed together, and you keep them mixed together for a long enough time and until they release, they actually immediately turn very dark colored. So we're thinking, oh, okay, yep, there's nitrogen and carbon dioxide aplenty all over Triton. That's probably what's going on here as well. The chemistry checks out. We also see the same kind of blackening geysers on Mars as well. So we're able to confirm with a completely different planet on the other side of the solar system of what could possibly be going on here. Now, does Triton have an active ocean? That's still a mystery. So are these geysers from the ocean deep within or not? Still a mystery. And then Pluto, yay, Pluto, my favorite. So Pluto, definitely an interesting Kuiper Belt planet to be sure. So again, nitrogen, methane, carbon monoxide, and water ice. Very, very simple compounds going on here. This, I mean, by all means, most of the geology on Pluto is still a bit of a head scratcher though, but this one probably took the cake. Because this was snakeskin terrain. We had no idea what else to call this thing. So we called it snakeskin terrain for the longest time. Its official name now is called Tartarus dorsa. But how in the world is this thing even made? So imagine, if you will, then, a very tall, spiky, spirally, and I mean very spiky thing, as almost like a jousting lance going on here. But many of these just angled and spiking toward the sky and many, many miles up kind of deal. What could possibly be going on here on Pluto? And it's just found in this one part of Pluto. This is just the eastern part of Pluto. If I, let's see, I know I have a laser pointer here. There we go. Tartarus dorsa is only just this part right here. Found nowhere else on Pluto. It's just this little part on Pluto. So what could possibly be going on here? You know what's the weirdest part? We have these on Earth. That's what's interesting. Now on Earth, they're not as tall, thankfully. They're much, much shorter. But we found them in the Atacama Desert in South America. So these are actually called Penitentes. So Penitentes are where you have just a very natural ice block, and then the sun has to hit it at just the right angle for it to be that spiky. So someone did a beautiful model of those Penitentes on Pluto. The math checked out. Ta-da! So it had to just be the right sun angle in that part of Pluto to get the spikiness and the angles and everything. So who would have thunk that we would find something on Earth of all places to have an analogy all the way out at Pluto? Ha! So this is an interesting part of Pluto as well. This is on the western shores of Sputnik Planitia. So Sputnik Planitia is this the big, beautiful heart basin. All of this stuff is just jumbled up crinkly, cracking mountains, which we do call chaos terrain because we don't know what else to call it. This is an example of a beautiful, lovely glacier here. This is called Barre Montes because there are little squiggly mountains here on this to So a little tidbit fun fact about me. I actually got to name this glacier and this hole to the south part of this glacier called Hecla Cavus. So I got to name those on Pluto. I also got to name 2 fault systems on Pluto, Hermod and Cacno. So big, beautiful fault systems just cracking the surface all over Pluto as well, which is neat. Then we found this guy on the southern hemisphere of Pluto here. So not so tiny. It's fairly large for considering the size of Pluto, though, but relatively small otherwise. This thing is only like 3 or 4 kilometers big, so really tiny, really short, but still spectacular. So this is considered to be a cryovolcano, and in the truest sense of a cryovolcano, because it has a vent. This thing is elevated upwards into a ring, and then all of this little knobby stuff all over the place might have been it's lava just kind of spilling out and crinkling all over the place. And then just to the south of that small one I just showed you was Right Mons, which is this one. Just to the south of that, might be another one called Picard Mons. So 2 possible volcanoes going on here. Now, again, I work on a little bit of the chemistry, a little bit of the physics, the mineralogy, the geophysics. What could possibly be cryolava at negative 400 some degrees Fahrenheit? And so the unfortunate part is we still don't know a lot about ice in a laboratory setting. So a lot of this is just models of what little knowledge we have currently. What I was personally able to figure out, though, is that if you have water and methane, that's the best combination you can have. You can have very strong mountains, and you can have ridges and very dynamic fault systems with water, ice, and methane. Now, if you have way too much methane and some ammonia with it, so the same ammonia we have here on Earth, cleaning products, ammonia. If you have more ammonia into the mix, that's bad. The more gooey and sticky and maybe even runny, it's not going to congeal. It's not going to build up beautiful mountains and volcanoes and everything. It's just going to be very puddly and just gooey kind of deal. So that's unfortunately all we know about the chemistry so far. Who knows? Who knows where experiments are going to be in the future? And then I'm going to end it off with Charon, which is Pluto's largest moon. There's 5 different moons of Pluto, though, but Charon is probably our best imaged moon so far from New Horizons. But it's a really interesting moon in that the top part of it looks very weathered and cratered and kind of old, whereas the bottom part, definitely more craters too, but it looks smoother. It's almost like someone had a jawbreaker, but some other little weird, interesting tidbits here of geology, just some of that canyon system near the equator. And this little guy has a belly button, guys. This is just a tiny little mountain that may have just sunk, being like there might be some faults around this little mountain to the point where it just kind of sunk whole, this poor mountain, into Charon. So, oh well. But if anybody is interested to know more about the geology or the chemistry and the physics and the mineralogy of Pluto and the whole Pluto system, a textbook was just released just last year about everything that New Horizons has observed and found so far. And then we have some more really interesting ice missions coming up. So Artemis Artemis, we don't necessarily call it an ice type mission, but Artemis is going to be our next generation of boots on the ground, bringing astronauts back to the moon. And so we want to bring astronauts to the south pole of the moon. That's where all the cool water ice and other kinds of ice is, at the moon. So Artemis, we are now developing what kind of instruments the astronauts would need to have to study the ice at the moon. We also have Viper. Viper is going to be a really cute little rover to be launched, I believe, mid to end next year already. They're still in planning stages and it's currently being built, but Viper is going to be a cute little rover with a little core drill in its stomach, and it's going to core drill into bits and pieces of ice on the moon. And so those little core drilling bits, it's going to essentially just eat little bits and pieces of the ice at the moon. It's going to have a little chemistry lab in its stomach, and then it'll just spit up the ice and move on, and then take another sample. So wine tasting, it's like ice tasting for this little rover. Swish and spit. You have Europa Clipper. So Europa Clipper, there for a while, got all sorts of bad luck with funding and change of management, and this poor mission was just having the worst luck. But it finally has a ride. As of just a couple months ago, we just confirmed that Europa Clipper now has a rocket to lead it to Europa. So it has a ride now. Hooray. So it's on track. Everything's fine with its funding now. Just there for a while, it was just like, oh, is it going to happen or not? Dragonfly. Oh, this is going to be a really interesting mission. So this is going to be the first quadcopter, very large quadcopter, and it's going to go to Titan, Saturn's moon. So we already picked out where we want the drone to go to on Titan, but it's going to have its own little chemistry lab, again, in the stomach of this drone, but it's going to hop around the surface of Titan. It's going to be so cool. So unfortunately, COVID really delayed some of the design work for it, but they're back up and running, and they're testing the blades right now, make sure blades can handle not only cold, that's an obvious one, but there is a lot of ice particles, those dunes all over Titan. That's going to be a bit of a hazard because you're going to have ice just kind of flip-flopping around. You don't want any of that to get stuck in your rotor system. Your drone is going to be grounded forever. So I'm going to leave it off with this slide, though, and this current research questions could be like a mile long, to be sure, but all sorts of different things. How were ices in the early solar system? So while planets were forming, what kind of chemistry and ices were we dealing then versus now? Are there different ways to sublimate the ice or radiate the ice? Are there different ways to melt the ice? What kind of different conditions would you have with different kinds of geysers or different kinds of cryovolcanoes? When I mean by exogenic and endogenic, I mean, does the process of the ice bending and geysering and slopping all over the place, is it internal, or is something happening on the outside of this moon that's making the ice bend and curdle and everything? And then how do we be better about our experimental research too? Like I said, very cold experiments are extremely difficult, but not impossible. So what kinds of instruments, what kind of laboratories can we maybe get on the ball in the future? But thank you so much for having me tonight. I love talking about cryogeology and happy to answer any questions anybody may have. Thanks.
Caitlin, we had one question from a participant in the chat box, and it says, how did you come up with the names for those features?
I'm so glad someone asked that question. So interestingly enough, whenever you want to name a feature on a planet, asteroid, comet, you name it, there's rules, because heaven forbid you name a crater after your cat, because no one wants to write a mission proposal to study Mr. Snuggles' crater. I mean, that would be fun, but we wouldn't get anywhere. So there's rules upon rules upon rules of themes. So this is brought about by the International Astronomical Union, the IAU. So think of the IAU as kind of like our astronomy version of the UN. They're the ones who set the rules. They're the ones who set the whole naming rule for Pluto being a dwarf planet. Unfairly, if I may add. But regardless, they're the ones with the rules. So if you're wanting to name something on a planet or moon, they will give you a 90-page PDF rule book, and then you need to follow by those themes. So for example, Barre Montes. So Montes means mountains. And then on Pluto, mountains must be named after historic voyaging people in history. So Barre was the first woman to circumnavigate the globe. Whereas Hecla Cavis, Cavis means cavity or just strange hole. So cavities, yes, Pluto has cavities. Didn't brush enough. So cavities, cavi on Pluto need to be named after the gates of hell through literature, mythologies, whatever. So Hecla is a Germanic medieval gate to the underworld, and it was probably the easiest one I can spell as well. So it was kind of out of convenience in that regard too. And then the others, it's all themes, and it's really entertaining to see what all kinds of themes are out there too. Asteroids probably have the weirdest naming themes out there. I won't get into too much of it, but I will tell you probably the weirdest asteroid. Actually, you know what? Two asteroids. One is the asteroid called Stein. And Stein, any crater or boulder feature on Stein is named after a gemstone. So you guys might appreciate that. So there's like a topaz crater and an amethyst crater and a citrine crater and so on. But probably the weirdest crater out, or the weirdest naming scheme out there, is on the asteroid Gaspra. I don't know who came up with this theme, but whoever it was, I don't know whether I want to shake their hand and give them a cookie or just kick them. But the theme for this asteroid is named after spas and resorts of the world. What kind of theme is that? I will never know. No one knows. It is entertainment for the rest of us, but I don't study Gaspra or much in the way of asteroids regardless. Okay, do any of the outer moons have rocky cores that could affect the surface dynamics by heating? Yes. So that's the fun part, right? Is, are these cores still active? And then are some of the cores active, but by tidal pooling? So the core of Triton is very much being pulled all over the place by Neptune, because Neptune is so large and it's drawing Triton. It's spiraling inward and whatnot. So the poor insides of Triton right now are just like nervous Nelly over there. Whereas the core of, say, Enceladus and Titan, they don't get jumbled that much by Saturn. They're very, very far away enough from Saturn. They still orbit around Saturn. They're still moons, but their insides are not being jostled that much by Saturn. Now, Enceladus could actually still be jostled by Saturn, but Titan, not so much. But that doesn't necessarily mean that the core could still have some sort of internal heat. So we would call this radiogenic heating. Or like Pluto, Pluto's core, we may think that Pluto also has a very interesting ocean as well, but there's no tidal pooling of any sort at Pluto. So what we're thinking is the inside of Pluto is very radioactive, and that stuff will stay very slowly heating the inside of Pluto for quite some time. the Sandals gas prize. Thank you, Olivia. Let's see. Yeah, any other fun questions about ice? This stuff is really quite fascinating, to be sure. I will tell you one other fun thing about ice on Mars real quick, and then maybe I could even find a quick picture of it too. But there's an interesting little process on Mars called spiders. Let's see if I may not have a picture of it. Maybe I do. Just in case, if I don't, I'll tell you what Mars spiders are regardless. So Mars, like I had shown previously, had frozen dunes. Now, when those dunes freeze over, it starts to trap a lot of nitrogen and carbon dioxide into the dunes. And so when those dunes start to, I found it, thaw. Oh dear. Well, hang on. My computer started to not like me at the moment. There's Mars. There's Mars. Yeah, there we go, there we go, there we go. All right, so those are spiders. So that nitrogen and carbon dioxide, whenever it becomes springtime on Mars, that frost will thaw out that nitrogen and carbon dioxide, and it makes little tiny puffs, tiny little geysers, just puffs of black smoky looking stuff. But we call them spiders because they move so quickly. They look like that they're skittering across the surface here. So the interesting part about people who study Mars is that we always know when it's springtime. When the Mars folks go, the spiders are here. We always know it's springtime for those folks, and we're like, oh, okay, good for you. Spring is here, I guess, on Mars whenever the spiders arrive. Now, when I mean they don't last that long, they only last for a couple of days until the winter season comes again and frosts over all the dunes, and then the process starts over again. So the more official term for these are called araniforms, but or anariforms, something like that. But we just love calling them Mars spiders because why not? So some very bizarre geology going on in the outer solar system, to be sure.
Anybody else have any questions? Okay, well, if you don't and you want to exit, it would be, let's just do a quick one question quiz to document your attendance. And that would be, if everybody could answer the question, is from Caitlin's talk, how many forms of ice are there? You can get it wrong or right, just give us your best answer. Yeah, they were paying attention.
That makes me so happy. Yay.
Chris, how could you not? That was such a fantastic, awesome presentation.
Thank you.
Really, really awesome.
Yeah. Oh goodness. Yes. Planetary geology is certainly interesting, to be sure. And another interesting thing too that y'all might find interesting too is we send a lot of planetary geologists out in the field all over Earth. We have to use Earth as our own playground. So I'm actually going to be helping a rover team heading out to New Mexico in October, I believe. So, but we're got to do all the planning now, and I'll be helping simulate our some like simulation astronauts out there, and they're gonna test drive a rover out in New Mexico. So exciting times though, but we always have what's called analog astronauts. There's some beautiful geology here on Earth that we need to take advantage of, to be sure. So Iceland and Hawaii are like the best analogs for volcanic systems on Mars. Great examples.
I think there was one question I saw. It scrolled by in the chat. How many
Oh.
forms of ice exist at approximately 1 bar?
I believe 2, but it depends upon your temperature. So your high temperature versus low temperature at 1 bar, I think there's 2 different water ices that you can play around with, but they're not terribly spectacular, but very normal, very normal ice. It's either the very extreme cold low pressure ones or the extreme low pressure or high pressure low temperature ones. Very tricky to try to make in a laboratory, but yeah, you know what? That's what we got to do.
All right, anybody else? Well, it looks like we may have exhausted our questions tonight, Caitlin. I just want to say on behalf of everyone, thank you so much, and I hope we can get you to come back and talk on a different topic another time. It'd be really great. We'd love to have you back.
Oh, I'd love to be back. Maybe next time I'll just talk all about Mars geology, and all the cool stuff we're doing with the rovers and deltas and river systems on Mars. There's some cool stuff there too.
I was trying to find something here quick.
Chris, while you're finding something, I just wanted to let everybody know that they'll have their certificate within a week.
Okay, great. Thank you, Cheryl.
You're welcome.
Oh, I saw a quick question. What drew you to study this subject? Completely by accident, honestly. I started out doing seismology work for quite a while. I was doing seismology in the Appalachians, and then did radio astronomy for a couple of years. Got sadly bored out of my mind with that. I landed with an internship out in Arizona to do Mars geology, and immediately fell in love with planetary geology, and did Pluto and worked with the New Horizons mission folks for my PhD. And now I'm doing Moon, currently at NASA, but also they allow me to still dabble everywhere in the solar system however I please.
Cool. We had a few months back, Dr. Glotch did a presentation on the LRO, and he said that you would not disappoint, and you didn't.
Oh.
He said you were real cool.
Probably pun intended there.
Oh yeah, likely so.
Yeah.
Well, that may be the end of our evening tonight. Just as I said, you know, if you're exiting, please make a note that you were here in the chat box, and we hope to see you again soon.
Yeah, and thank you so much again for having me this evening, and I hope to come back and maybe chat about Mars next time. Yeah.
I guarantee we'd like that. Thank you so much.
Thank you. Everyone have a nice evening.
You too. Take care.